first revise what we did so far. Just a quick revision. So we defined analytic functions. Okay?
Yes, sir.
These are functions which are complex differentiable at a point and some neighborhood around this point. Okay? So we complex differentiability here and around some neighborhood, no matter how small the neighborhood is. Okay? Now, so f of z is analytic, obviously if it is complex differentiable at here and some neighborhood around it, and complex differentiability was that this limit should exist, limit delta z equals to 0. So this is f prime of z, f of z plus delta z and this f of z divided by delta. Okay?
Yes, sir.
So by what do we mean when we say that this limit exists? That it should be independent of direction. Direction. Yeah, exactly. So that would mean limit h approaches to 0 operationally this would mean like this: z plus h e power I theta minus f of z divided by h e power I theta. So this thing should not be a function of. No, what should it not be a function of for it to be direction independent? Theta, right? So so whatever answer you get should not be dependent on theta, right? Because there are multiple ways you can approach this point, and all can be characterized by this angle theta. Okay, right? So delta z is h equal I to theta. We are approaching z through a direction theta. Okay, so this thing should be independent of theta. Then you say that the function is what? Complex differentiable. So you need complex differentiable plus there should be a neighborhood in which around this point in which this function is complex differentiable, and then you can call it analytic at that point. Okay? And then you saw that a necessary condition, right? We saw that a necessary condition for this for complex differentiability to hold is that it should satisfy Cauchy-Riemann, right? But it's not a sufficient condition, right? Cauchy-Riemann does not guarantee you, complex differentiability. Neither does it guarantee you analyticity. Okay? Huh? So if I am to show it pictorially, there is a class of functions which satisfy Cauchy-Riemann at a point. Let's say at a point some z naught. Okay? There is a big class of functions which would satisfy Cauchy-Riemann. Okay? Huh? Cauchy-Riemann, you remember?
Yes.
Right? Then there is a smaller set of functions inside this class of functions which are complex differentiable. At that point. Okay? Huh? Yes. Then there is even smaller set of functions which are analytic. Okay? So if you go the other way around, so analyticity at a point implies complex differentiability, which implies Cauchy-Riemann. But if you want to go this way, Cauchy-Riemann plus your partial derivatives should be continuous. Okay? Okay? I'll qualify what do I mean by partial derivatives to be continuous. Cauchy-Riemann plus continuous partial derivatives implies complex differentiability, right? And complex differentiability plus complex differentiability around a neighborhood gives you what? Analyticity, right? So analyticity implies, this is talking only at a point, okay? Then you need to check it every other point, okay? So analyticity implies what? Complex differentiability, which implies Cauchy-Riemann, okay? So these things are okay. But if you want to go the other way around, Cauchy-Riemann plus what? Continuous partial gives you what? Complex differentiability, right? And complex differentiability plus around a neighborhood, right? Neighborhood of a point, including the point also, right? A neighborhood, whatever implies analysis. Okay? Right? So is this clear?
Yes,
is the structure clear? What implies what? Right?
Yes.
So one quick way to suspect whether a function is analytic or not is that it should be just a function of z. Right? If you write any function of z, right? Remember what I taught you, that would imply, so any function of z would directly satisfy this, right? Because there is no z star inside it. Remember, z and z star can be thought of as coordinates, right? And you can take partial derivatives. Okay. This is basically implies Cauchy-Riemann, right? This is Cauchy-Riemann written in a different way. Okay, written in a complex manner. Okay, so this is basically what the function satisfies Cauchy-Riemann. So this a function, a necessary condition for a function to be analytic is that it should be only a function of z. The moment you see z star, you should suspect that okay, this cannot be analytic. Okay, but if you just see z, yeah, this may be analytic, provided other things, right? Yeah? But usually in physics problems, if you see a function of z, it will most likely be analytic, right? Okay. So let's learn some examples. Okay, let's learn an example which is complex differentiable. So it automatically satisfies Cauchy-Riemann, right? But not analytic. Okay, right? Here, for a function here in this, in this region. And in fact, we have already seen a function. It is f of z equal to mod z square. Right? Remember this circle I had drawn. The circle I had drawn only at a point, and the point that I am talking about is z equal to 0. This is the point I am talking about. Okay. So at z equal to 0, you will find that this f of, remember we did in last class that this f of z is complex differentiable, right? Huh? Right? If you compute this limit h approaches to 0, f of z plus h equal I theta minus f of z divided by what? H equal I theta around z equal to 0, right? So this will be 0 because you have to compute at z equal to 0, right? So this will be 0 because mod z square, right? And this will be what? Mod h equal I theta square, that is just h square, right? Equal I theta mod is 1 and divided by h equal I theta limit h approaches to 0, right? So one h will go and there will be a h in the numerator because of which it will be 0. Okay? You see, operationally this is independent of theta. There is no theta dependency. Final answer. So this thing is what? Complex differentiable. Okay? So that would automatically imply it satisfies what? Cauchy-Riemann. It satisfies Cauchy-Riemann. But it's not analytic. Right? Why is it not analytic? Because there is no other point around z equal to 0 where it is complex differentiable. Right? So the neighborhood is missing. It is a complex differentiable here, but you can never draw a region around this point where the function would be complex. Yeah. So when I say a region, you should assume just small disk around this point. So that's typically what people do. Okay, because at any other point it's not complex differentiable. It's only complex only at z equal to 0. Okay? But then we can ask, what does just Cauchy-Riemann guarantee? Okay? What does Cauchy-Riemann guarantee? Cauchy-Riemann just guarantees that the function has same derivative, okay, if you go along the x-axis and along the y-axis. In fact, I will leave it to as a homework, right? So take this complex function, okay, find its derivative if you come. So basically do this for theta equal to 0, right? So you have to do this for theta equal to 0. You do this guy, compute this guy for theta equal to 0. Not for this function, for any function in general. Okay. If you compute this guy for theta equal to 0, you will get some answer. Okay. And the answer you will get is ux plus ibx, something like this. Okay. Now then you compute this guy for theta equal to for what theta you should compute it if you want to reach the point exactly pi by 2, right? So compute this guy at theta equal to pi by 2. Theta equal to pi by 2. Okay? What you will get is, okay, I will just write the answer. You will get v1 is v1 minus no wait, get u by you will get is you will get at theta equal to pi by 2, you will realize that you get this. Okay? Do this at home. Okay? Now, if you want your function to be complex differentiable, right? At least first check would be that these two should be same. Right? If you approach from theta around 0, along x-axis, along y-axis, वो दोनों same होने चाहिए. That's the first thing, right? You will ask. Only then you will talk about arbitrary directions.
Yes, sir.
So if you equate these two, you will get ux should be vy, real parts, and vx should be minus uy, which is the Cauchy Riemann. So Cauchy Riemann just guarantees you that if you approach along x-axis and along y-axis, okay, basically real axis and imaginary axis, then the derivatives are same. Okay, but it doesn't guarantee along all. Right? That's why Cauchy Riemann is a necessary condition. Because if Cauchy Riemann don't hold, then there are two directions in which the derivative limit does not exist. Derivative limit gives you different answers. Okay? Yeah, do this. Okay, do this. So you compute this object at theta equal to 0 and then theta equal to pi by 2. You should see this. Obviously, you have to break your function in real and imaginary parts to see this. Right? U plus iota. Okay? Is that fine? Huh? This is what this guarantees. Okay, let's go back to learning some examples. So you saw mod z square, it is complex differentiable, but not it's complex differentiable, but not analytic. Right? Now we'll learn a point we'll learn about a function which is, an example of a function which satisfies Cauchy Riemann, right? Cauchy Riemann is true, but the function is still not complex differentiable. Okay? What could be the reason? That the partials are discontinuous. Okay? So I'll give an example, and I'll give one more example for you to work out in your assignments. Okay? So let's consider this function. Yeah, you probably, most likely you'll never see such a function in physics. Okay? Well, at least not in undergrad physics. Maybe in research it might appear somewhere. Let's say z bar square divided by z not equal to 0 and z equal to 0. This kind of a function. Okay? So it is 0 and z equal to 0. For all the other points, it's z bar square divided by z. Okay? Huh? Let's compute its partial derivatives and show that it does satisfy Cauchy Riemann. Okay? Right? So to check Cauchy Riemann, I need to find the real and imaginary parts of the function, right? So what is f of z? So obviously at z equal to 0, the real and imaginary parts are 0 and 0. At z not equal to 0, they are a bit more non-trivial. So what is f of z? Is z bar square divided by z. So this is 1 divided by mod z square times z bar cube, right? I divided and multiplied by z bar. Okay? That is what? 1 over x square plus y square and x minus y whole. Okay? Is this fine? Fine? Okay. Now how about u? What should be u? U of x comma y? It should be 1 divided by x square plus, it's the real part of the function, right? 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 So I can write it like this, x minus iota y whole cube plus x plus iota y. This is the function and its complex conjugate, z. The real part of the function is just sum of the function and its complex conjugate, right? Okay? Or you can just expand this cube and collect real and imaginary parts separately. That will give the same answer. Is that fine? And what about v? Oh, then I need to divide by 2, so half of that. Remember? So what should be v? 1 divided by 2 iota x square plus y square. The same thing, but I have to put a minus sign. Minus x plus. How about now? Is this okay?
Yes.
This is fine, right? Huh? Or you can just expand and collect the terms which come with iota, and then you are basically done. That will give you the same answer. Okay, now let's compute partial derivatives. Since the function takes a different value at z equal to 0, so I have to be very careful, okay? So I have to go back to the first principle definition of the derivative. Right? Huh? Okay? first principle definition of the derivative. What is that? So what is u? So I want to check Cauchy-Riemann at z equal to 0. I will show that at z equal to 0, Cauchy-Riemann holds, but the function is still not complex differentiable. Okay. So ux, I want to compute ux at 0, 0. Okay, the partial derivative of ux at 0, 0, which is just limit h approach to 0, u of 0 plus h, 0. Because why I am keeping y would be a constant when you take partial derivative with respect to x. Huh? So y would just be a constant. Basically 3x square. So 3 you can think of as y. Okay, when you are taking partial derivative with respect to x. Huh? Okay. So now, so this is this and minus u at 0, 0 divided by h. Okay? Is this clear? So this is the partial derivative with respect to x. And what do I get? So what is u at h, 0? So this is not, obviously this is not the z equal to 0 point. It's something away. Then I have to use this definition, right? Okay. So y is 0. So y is 0 and x is some small number h. Okay. So what does this give me? U of h, 0. Yeah. So I'll get 1 divided by 2h square from here, right? Huh? And I'll get h cube from here and h cube. 2x h cube. 2x h cube. Now this guy is 0 because at z equal to 0 the function is just 0. Okay? So it means u and v both are 0. And there is 1 by h. Right? So what does this give? It gives 1. Right? This is 1. So ux, the partial derivative of x, computed at 0, 0, it gives you 1. Okay? Simple. Right? Now let's compute but let's compute uy. Let's compute all of them. Because eventually ux, uy, I'll compute vx, vy. So this is limit h equals to 0, u of 0, 0 plus h minus u of 0, 0 divided by what? What should I divide with? H. Right? So now, for this thing I have to use this definition. So I will get 1 divided by 2h square. No? This just vanishes. So what do I get? Limit h equals to 0. 1 divided by h is its own. And then I get 1 by 2h square. And I get x is 0. So I have to cube. I have to cube is what?
Minus 1. Minus
Minus iota, then it becomes plus, right? Or divided by that's 2 iota x. Yeah? And then I have to keep it minus iota. So it's just 0. It's just this factor vanishes at x equal to 0. No? Okay, good. So compute 2 of these, we also need vx and vy, right? 0, 0. What should be vx at 0, 0? It is limit h tends to 0. V of 0 plus h, 0 minus v of 0, 0 divided by h. This guy, right? Huh? V of 0, 0 is 0, right? You are exactly at this 0, 0 point. This you are slightly away, so you need to use the other definition, right? Huh? Just do it and you will find
1 by 2.
You will find 0. If you put h here, you will find 0. Okay? If you do it. Similarly, you do vy 0, 0, you find it to be 1. I won't repeat because it's the same thing. You just need to use this guy. Okay? Huh? Okay. Is this fine? Now, see, ux is what? At this point, 0, 0, it is 1. So is vy. So ux at 0, 0 is the same as vy at 0, 0. Excellent. Okay? Also, you see, uy at 0, 0 is basically minus vx at 0, 0. They're both zeros, so I can put a minus sign. Okay? So does this function satisfy Cauchy-Riemann at this point, 0? It does, right? Now let's check if it is what? Complex differentiable. You'll find it is not, right? Because you can immediately tell me that there is a z bar sitting, right? The z bar of f is not equal to 0, right? Or you can just do the first principle definition, h e power I theta. You will see that it is not differentiable. Okay? Alright? Huh?
Yes.
But you will still find that theta equal to 0 and theta equal to pi by 2, the derivatives are same. It takes the same value. Why? Because Cauchy-Riemann are true. Cauchy-Riemann at least guarantees you that if you approach along the real axis and imaginary axis, the function derivative gives you the same. Okay? Huh? Okay. And why did this happen? Why did Cauchy-Riemann hold but the function was still not complex differential? It's because partials were not continuous. But how did you know partials were not continuous? Okay? So I'll tell you what to do so that you can check. Okay? You find ux at any point x comma y. Okay? So it means whatever function I wrote, you just take its partial derivative and then compute this. Limit x approaches to 0, limit y approaches to 0. Okay? Okay? You take x going to 0 first and then you take y going to 0. Okay? It will give you some number. Okay? And then you do limit y going to 0, limit x going to 0. ux. Okay? This guy. Right? These will give you different answers. These two won't be same. So that's to say that the partials are not continuous. Okay? Right? This is very elementary calculation, so I leave it up to you and I hope you do it. Okay? So do you know what to do? Huh? Do you understand? Huh? You just take this function, whatever, one of them, this function, this guy, differentiate it with respect to x, keeping y constant. Okay? Then take two order of limit. Limit x going to 0, y going to 0. And then y going to 0, x going to 0. You will see that you will get different answers. Okay? That's why this function is not what? Complex differentiable. Okay? Huh? But still it satisfies what? Cauchy-Riemann. Okay? So just to revise this finally, that analyticity guarantees complex differentiability guarantees Cauchy-Riemann. Okay? But the other way around, it's not true. You have to be careful. Cauchy-Riemann plus continuous partials gives you what? Complex differentiability. And complex differentiability plus a neighborhood gives you analyticity. Okay? Yeah? Okay, good. So I hope this is now clear, crystal clear. Well, yeah, maybe it is. Okay. Good. Now let's move on. Let's try to expand like we did for real functions. We expanded a function around what? Around some point. Okay? I'll do z equal to 0. I'll expand the function around z equal to 0. You will try to expand it around any point. Okay? I'll just do z equal to 0. Expanding a function around any other point is just a shift. It's just a shift. You shift the function and do the same business. Okay? Shifting, I have told you how to shift functions, right? Just replace the argument with x minus x1. Okay? And clarify it a bit more. So let's say I have a function f of z. Okay? And let's say it's, what do we take the first what do? We take the function to be analytic. Okay? By now you must have realized that analytic functions, you can, almost get away with anything as long as you treat, you treat analytic functions as real functions and you can just get away with anything. You can integrate them as if they were real functions. You can differentiate them as if you're dealing with real functions, right? So for now, let's just do analytic. A function is analytic everywhere on the complex plane. Okay? What did you do for the real functions? Because intuitively I should do the same thing. For any real function f of x, if I want to expand it, let's say around x equal to 0, I wrote it like this, sum over n comes from 1, 0 to infinity, a n x to the power n. Okay? Then how did I find these a n, these coefficients? What did I do? Fine. Let's say, let me write it down. F of x
Derivatives.
Yeah, derivatives. Yeah. 1 plus x square. 1 plus ax
square plus
a1x plus a2x square plus so on. Right? How did I do? Huh? I take the derivative of the function and compute the derivative where? At x equal 0. The point where I am expanding. Okay? If I were expanding at any other point, so I shift the function, so x minus x naught square, and then I compute the derivative at x equal to x naught. Right? I'll just do 0. You guys please do at x naught. Okay? Huh? So if I take the derivative of the function df by dx, so what do I get? So first, oh no, this should not be 1. This is a0. This is the first option. Now, first if I substitute x equal to 0 directly, so f of 0, the function evaluated at 0, okay, is what? It's simply a0. Okay. Remember, you are getting a0 as some function, as this function evaluated at some point, right? So you know this function in some other representation. Okay? From that representation, you are trying to get a series representation. Right? For example, I tell you expand sine x. So you already know the function. One representation of the function. Okay? Then using this representation, you evaluate this representation at x equal to 0, which gives you the first, right? a0. The first term. Okay? Yes. Now, so a0 is f of 0. Okay? Then, if I differentiate, this a0 will go, right? And I will get a1 plus a2, sorry, 2a2x. And then I evaluate again at x equal to 0. So I get do f prime and then evaluate it at x equal to 0. Okay? That gives you what? a1. Alright? Similarly, f double prime, you would have to divide 1 with 2 factorial. Okay? If you remember. 0. Okay? Because each derivative will bring down the power and those powers will accumulate here. Okay? Yes. So if I generalize this, what do I get? An is what? 1 by n factorial nth derivative, so dn dx to the power n, but evaluated at where? X equal to 0. This is very necessary, this evaluation. It just tells me that these guys are just numbers. a0, a1, a2, these are just numbers. Okay, let's go, let's do it here. So if my f of z is analytic and I am expanding it around z equal to 0, it's analytic everywhere, okay? Then I can still write n runs from what? 0 to infinity an z to the power n. And how do I compute an? Okay? How do I compute an? Huh? Yeah, what?
This is real.
Derivative, yeah, exactly. This is whatever. So 1 divided by n factorial dn dz. Z computed where? It's very important. This guy. You just compute this function at z equal to 0. Okay? And that will give you the nth option. Okay? Huh? This is called Taylor series, right? This thing. This has a name, but I'll introduce that name later. Okay? Not right now. Okay? Huh? So obviously this function, since it was analytic, I was able to write it like this. Okay? Yes. Huh? We'll introduce one non-analytic point shortly, okay? But for now, let's think of it a bit more, okay? Complex functions, when you do this, the complex functions give you another way of figuring out these ans, okay? So your f of z is this, f of z, let me expand it out so that it's a bit more clear, but you guys should repeat this summation thing at your home. a0 plus a1z plus a2z square plus 1. Okay? Now this function is perfectly analytic, right? These are just powers of z, just functions of z, right? Everything is fine. So if you check, so this series, right? If it converges, then it's perfectly analytic. Okay? What about this guy? F of z by z. What do I get? a0 by z plus a1 plus a2 z square, right? A2 z. Okay, no, instead of doing this, let me just do one thing. Before doing this, let me just integrate this f of z over any curve, closed curve. Okay? Huh? So what do I get? Integral over some curve, f of z dz. What do I get? Huh? I'll put this, plug in this, right? What do I get? A0 will just give me 1. So
A not Z. A not Z.
huh? What do I get? A not?
A not Z.
No, I'm integrating out a closed curve. It should give a 0. Yeah, no, this should give a 0 indeed. But if I plug in this series, what do I get? Yeah, it should give a 0, right? But this guy should be 0 because the function is analytic. Good. Okay? Huh? Okay. Yeah, fine. Now, what about if I divide f of z by z? What do I get? A0 by z, right? Fine. Plus a1 plus a2 plus
A3 is
right? Now let me integrate this guy now. Integrate this guy over a closed loop around z equal to 0. Okay? What do I get? I'll get a0 integral f of z by z dz. No. Integral 1 of z dz plus a1 integral dz, right? Plus a2 z dz around this loop plus so on, right? The powers of z. What do you know these integrals? Have you seen them? Right? Which one will survive? Remember, we've done these integrals, right? These integrals. So what is integral around a closed loop which encloses origin of dz by z to the power n? What is this guy? 2 pi. Yeah, 2 pi I, but only if delta I. If n is 1.
Yes.
So all of these are what? 0. All of these vanish except what?
First one.
So I will get a0 times 2 pi I. Okay? Huh? Right?
Yes, sir.
In fact, this is why this function integrated over a closed loop gives you 0. Why? Because if you do, right, there is no non-elasticity anywhere, so it just gives you 0, right? एक करके करोगे तो all of them will walk. These are just integrals of powers of z around this closed loop. Whatever closed loop you consider, doesn't really matter. Okay? Fine. And so from here I extract a0. What is this? Integral around a closed loop dz. Right? Remember, a0 came out because I deliberately produced a non-analyticity by dividing by z. F of z is analytic. Right? Z is not. 1 by z is not. Right? Even to product that point of non-analyticity, z equals 0 survives still. Right? Okay? So I got a0 out of it. Right? Similarly, if I want to get a1, what should I divide? With
Z.
I want to get a1. So a1 के नीचे आना चाहिए 1 by z. So what should I do? Z square. So if I want to get a2, what should I get? Z cube, right? So if I want to get an, what do I get? What should I divide with? I should integrate 1 divided by 2 pi I. I should divide by 1 by 2 pi I, but I should divide f of z by what?
Z
plus 1. Right? I should do this, right? Because you know that f of z is a series, right? In powers of z. Huh? And when I divide by z to the power n plus 1, when I divide by z to the power n plus 1, right? The coefficient of a, the thing that will come with an plus an would be 1 by z. And when I integrate over the loop, only that will survive. Rest will just vanish. Whether they are positive powers or negative powers doesn't really matter. Okay? Good. So this is the an. So complex functions give you, and analytic functions give you another way of figuring out this, right? An. Okay? So then, but then you shouldn't have two different answers, right? So this should be same as 1 by n factorial, right? D. Computed where? Here you don't need to compute, you just need to compute this integral over some circle, over some loop. You may take it circle if you wish. You'll get the same answer. Is this fine? Huh? So this is basically the Taylor series, if you wish, for complex functions. But this function is analytic. Okay? Now let's make this z equal to 0 non-analytic. Okay? Oh, by the way, if you are not expanding around z equal to 0 at some other point, what should change? What should change? Figure out what would change. Okay? Figure out and then, okay? You can figure that out. You have to integrate over a closed loop which around what? Z equal? Around z equal? Around the point, right? Around the point z naught. If you are expanding around a point z naught. I am doing z equal to 0, right? It's just a shift, so you replace that with z minus z naught. Exactly. Integral f of z dz divided by z minus z naught. Same here, you will compute at z equal to z naught. Figure it out. And the series will become series in powers of z minus z naught. Okay. Z minus z naught, z minus z naught ka square, z minus z naught ka cube. And just shift. Okay, good. Now let's make this. No, this function was analytic everywhere and you were able to do these things. Okay? Huh? Huh? Now let's then make this function to be non-analytic at z equal to 0. At z equal to 0, the function is not analytic anymore. Okay? But what kind of non-analyticity? It's an accelerated singularity. Because I'm telling you, I mean, yahi se bol raha hu, it's not analytic only at this point. Okay? So in the neighborhood of this point, it's analytic, right? So that's the definition of an isolated singularity. Okay?
Yes, sir.
And we want, okay, fine, it can be that. So if it is an isolated singularity, okay, then it can be of one of these three types, either a pole or a removable or an essential. Removable means that you can just remove it. So we won't talk about removable because removable singularity is not really a non-analytic point. You can just get rid of it by redefining your function. So let's leave that. So that leaves 2, right? So in order to deal with this, right, you include negative powers in your series because you know at this point the function should blow up. You include negative powers. Earlier you had only positive powers, right? Right? You had only positive powers because there was no non-analytic point. Okay, on the complex plane. Okay?
Yes.
But now you include what? Negative powers. Okay? So you write f of z. You write f of z as what? So on plus a minus 3 z3 plus a minus 2 z square plus a minus 1 divided by z plus what? A0 plus a1 z. Okay? A2 z square if you wish. You write it like this. Okay? Is this fine? Huh? What do I get? Let me just write it as sum over n runs from what? Minus infinity to infinity. An. Oh no. An. It's the same thing. When you put negative powers, this will be z equal minus 2, z equal minus 3, right? Why did we include negative powers? Why? Because I know the function is not analytic here. Okay? Huh? So this 1 by z will cause the function to blow up. Huh? Remember, if we'll figure out how to figure out these n, right? You'll see it has such essentially similar procedure. Okay? But you see that this part defines whether this singularity, this isolated singularity, is what? Is it an essential singularity or a pole? So if all the ANs are non-zero, negative ones, the positive ones are, we don't care, they just give analytic behavior. Okay? The negative ones are which are responsible for the non-analytic behavior there, right? At z equal to 0. So if all of the negative ones are non-zero, then it's not an essential singularity. Okay? If all of them are non-zero, then it's an essential singularity. Right? If only finitely many of them are non-zero, then it's what? A pole. Then it's what? Pole. Do you get my point? Yes, sir. Right? Then it's just a pole. And pole of what order? depending on कहाँ तक survive करेंगे. So if my a minus 3 के बाद सब 0 है, if after a minus 3 all of them are 0, then it's a pole of order 3. If it's only a minus 1 तक उसके बाद सब 0 है, then it's a pole of order 1, which is also called a simple pole. Okay? So let's first deal with that. Let's deal with that. Okay? Let's first deal with. No. We can do it together. Okay? Let me figure out what these A's are. Okay? What should I do? What trick did I use? Obviously, the differentiation trick won't work anymore. Right? Because when you take differentiation and then you want to compute the derivative at what z equal to 0, right? You are expanding at z equal to 0. These powers will cause problems. Hey, these will vanish, but these won't. You won't be able to get rid of them. Right? Okay? But the integral one would still work because you are avoiding z equal to 0. You are just integrating around it. है ना? So let's say I want to get. Let's say if I just integrate the function directly, what do I get? If I just integrate the function directly, integral dz f of z, what do I get? What do I get? So I have to integrate every term, right? I can just put plug this series here and integrate every term. Which one will survive? Which one will survive? A minus 1 will survive, right? A minus 1 will z. Rest are all 0. The powers of z. 0. Right? A minus 1 will survive. But what will I get? Integral over some loop around z equal to 0. Right? 1 by z dz. Which is just 2 pi. Right? This is 2 pi. This is 2 pi. This is a minus 1. Okay? So that gives me what? A minus 1. dz. Okay? Is this clear? So if you integrate the function, this function with single non-analyticity at z equal to 0, okay? What do we get? That the integral is equal to what? A minus 1. Right? Divided by. Yeah, there's a factor of 2 pi, just take that into account. Okay? So that's the reason why a minus 1 is called residue of the function. It's called residue. Okay? And the integral is always equal to the residue. Okay? This has a special name. A minus 1 has a special name. It's called a residue. Okay? And when you integrate a function, okay? I'm talking about function with a single with a single non-analyticity. Right? You need to look that inside. If there is a non-analyticity, you need to compute residue at that point. I'll show. We'll discuss how to compute this a minus 1. Okay? Right? For now, we are figuring out what these a's are. Right? We got one of them, a minus 1, and it was exactly equal to the integral of the function around some closed loop, right? Which surrounds this z equal to 0. This is perfectly fine, right? Because you are avoiding z equal to 0. You're just integrating around it. The derivative trick won't work here. Okay? Okay. Now, what if I want to get something else? Let's say I want to get a0. What should I divide with? And then integrate. What should I do? I should divide with what? Let's say I want to get a0. What should I divide with? I should divide with z, right? Then you know when I divide the function with z, a0 will get 1 by z, and then if I integrate, a0 will survive. Everything else will vanish. Right? Think. Right?
Yes, sir.
No? What if I want to figure out a minus 3? What should I divide with?
Z to the power minus
Minus 4. Z to the power minus 4. I should multiply with z to the power 4, that is dividing with z to the power minus 4. Right? So minus 4 plus 3 will give 1. Okay? So it's always 1 greater than the coefficient you want. So an, can I write an is just simply 1 to 2 pi. You integrate dz. You integrate f of a z. But now, you integrate a different function. You just manually divide so that there is a non-analytic point. That will become what? Is this okay? Right? See, it's the same formula. It nicely extends. It's the same formula. This formula will only work with what? Analytic functions. Completely analytic functions. Like analytic everywhere. But this formula nicely extends to non-analytic trees. Right? You don't need to worry about it. Yeah? Yeah? Okay? Because this derivative, you compute at z equals 0. If z equals 0 is non-analytic, cause problems. But this thing you're integrating around. Right? You're avoiding that point. And you get this formula. Right? So you can expand a function around z equal to 0, even if z equal to 0 is a non-analytic point, but you need to take into account what? Negative powers. So you will get n minus infinity, a n z to the power n f of z. This is what you get for f of z. Okay? Huh? And how do you find ans? An would be 1 divided by 2 pi I integral over some closed loop, any closed loop you wish, because you know you can deform your contour as long as you don't include any non-analytic point, which is okay because the only non-analytic point is z equal to 0. That's what we are dealing with right now. F of z divided by z to the power 1 n plus 1 is 0. Okay? This is called Laurent series. Laurent series. Okay? The other thing was called Taylor series extended for complex function. This is but that other thing is also Laurent series. It's just that a minus 1, a minus whatever, the negative are just 0. Okay? Now let's go back to this a minus 1 is integral. This guy, a minus 1, because this is a useful thing. It tells me what the integral of the function is around the closed loop. Right? Remember, if I think of this guy, f of z divided by z to the power n plus 1 as a single function, right, some g of z, right? This thing is essentially you are computing residue of this thing, full thing. Huh? Do you get my point? Because you know only 1 by z contributes. Right? So this formula is the same as this formula. It's just that the function is different. It's f of z divided by z to the power n plus 1. Okay, good. Now let's try to figure out how to get this residue. Okay? Without expanding. Okay. If your function has a pole of finite order, so that means f of z can be written as what? Let's say the order is n, so a minus n divided by z to the power what? N plus a minus n plus 1 divided by z to the power n minus 1 plus 1. Okay? Then a0, then a1z. Right? This is the analytic part. This is the non-analytic part. This is a pole of order. If you have a pole of finite order, okay, you want to get what? You want to reach this a minus 1. You want to extract out this guy. Okay? What should you do? The way to do it is to notice that if there is a pole of finite order, so a minus 1 इसके बाद कुछ नहीं आएगा, right? It does not extend to minus infinity. I can multiply with z to the power n, and the function becomes perfectly analytic. So this function, let's say g of z to the power n, f of z, is what? It's perfectly analytic. And it is series is this a minus n plus a minus n plus 1 z to the power what? Minus 1, z to the power z and z to the power 1 z plus a minus n plus 2 z square. Right? No, I just multiplied with z to the power n and defined a new function. This is perfectly analytic. Right? For perfectly analytic functions, right, we saw that there is another formula. What was that formula? That there is another formula to get these coefficients. Differentiation, right? Right? No? So I should differentiate this guy. Right? And which coefficient do I want? by what? A minus 1 z to the power what? N minus 1. Right? I am multiplying with z. What number coefficient do I want? This is the 0th number coefficient. This is the first coefficient, second coefficient. What is the number of this coefficient? It's called a minus 1 because okay, I have labeled it differently. Like labels came from here. But what is which term is this? It is the n minus 1 term. Right? Huh? So I differentiate this function. So d n minus 1 divided by dz n minus 1 of z to the power n f of z. Right? But you have to divide with factorial, right? This is what? What is this then? This is the residue of an nth order pole. Right? You just got rid of the z to the power n. You just multiply with z to the power n. Right? Huh? So when you get rid of it, then you can just deal with it, right? You deal with real function, right? Remember, this formula is easier than integrating over a loop. Okay? This formula is easier than integrating an arbitrary function over a loop. This is easier. This is derivative, taking derivatives is easier. Okay? But this works only when you have what? Poles of finite order. Poles of finite order. Right? Huh? Okay? Good. So what about if you have a simple pole? What about if you have a simple pole? So n should be what? 1. So 1 minus 1 is 0, so you don't need to take a derivative. So what is a minus 1 then? 1 minus 1 is 0 factorial, which is 1. So it's z for z. Okay? But you have to be careful. These formulas that I wrote are very ill defined because f of z blows up, right? At z equal to 0. Right? So that's why I need to write this line, limit z equals to 0. Right? Because f of z has 1 by z in it. Right? So z times 1 by z is just 1. Right? But strictly at z equal to 0, this is infinity, you are multiplying it with 0, which is not a well-defined operation. But if you compute this guy, then it is exactly equal to 1 because you are infinitesimally close to 0 but not really 0. So you can cancel these two. That's the only time you can cancel these two. Okay? Sorry, I said something wrong earlier. No, that was fine. 0 into infinity is ill defined. 0 into infinity is just 0 by 0. Okay? Because if I substitute 0, then it's just 0 by 0. Right? So this is the mathematically proper operation that you should do. This will give you a finite answer. Okay? And that would be your what? Residue. And I should do the same thing here. Right? Where should I take the limit? After the derivative or before the derivative? After the derivative, right? Because otherwise the derivative will become meaningless if you have already taken the limit. Remember, you have already taken the limit, there is nothing to differentiate anymore. A minus 1. 1 divided by n minus 1 factorial. Limit z equals to what? 0. Okay? Remember, if your similarity was at z equals z naught and you are expanding around that point, you just replace z with z minus z naught. Similarly here, replace z with z minus z naught. Okay, and limit z across to z naught. Please do it yourself. Oh, sorry, please do it yourself. Okay? So now what did you realize? That what did this Laurent series give us? Okay? It gave us an important point that if you want to integrate any function for z, any analytic function, it's just 2 pi times what? Times the residue. Times a minus 1, which is also called the residue. Right? Okay? Is it clear? And how do you find the residue? That if it's a pole of finite order, then there is a simple trick to find the residue. Right? This trick. Okay? But if the pole is not of finite order, if it's an essential singularity, then this trick won't work. Right? Because you cannot multiply it. What would you multiply it? Here you are able to multiply with it. You can't. Right? You can't do this. Right? So then you have to expand the function. You have to actually expand the function. and find these coefficients. Is this okay?
Yes.
Huh? Huh? We'll do some example later, but for now I just want to continue with this residue business. One last point and then we can conclude this class. Okay? Okay. So I had a singularity here, right? I can expand around this singularity, okay? But let's say I have one more singularity here. Okay? We'll learn later on that how do I expand when I have multiple singularities. Okay, what are the subtleties of this? Maybe in next class, hopefully. Okay. For now, I just want to integrate the function over this loop which contains both of these singularities. Okay? So I know if I just, this guy I know, if I just integrate around this, it is what? Times the residue here. Right? Remember, see, the residue is computed this. Imagine these are poles of finite order. Okay? Then the residue is computed like this. Right? Okay? If these are not polar, then you have to actually expand. Okay? If it's an essential singularity, then you have to expand and find the residue. Okay? Basically find a minus 1. What did you get for a minus 1? Okay. Good. So I know this. Right? I also know that if I expand around this point, that I also know. Right? Because I have to expand around this and find the residue here. If it's a pole of finite order, then I just use that formula. I'll get the residue here. Now I want to know what is the full thing if I integrate both. If I integrate over a loop which contains both. Huh? The answer, the way to do it is to use the same trick. You just split it a bit, connect it like this, and just do whatever loop you want to do, and then come back. Okay? So you add this, go like this. Okay? Sorry, not this one. Just come back like this. So these lines will cancel each other. Okay? These lines will cancel each other because you are going this way and then coming back. What will be left? So okay, what would be the total integral? 0. Why? Because you are avoiding all the non-analytic points, right? Inside is this. There is no non-analytic point inside. Right? So let me call this 1, let me call this 2, let me call this 3. I1 plus I2 plus I3 should be what? Right? Huh? Right? Right? I didn't take these parts because they just naturally cancel each other. Why? Because you're going like this and then coming back. Then coming back. Right? So that will give me what? I1 is minus I2 minus I3. So I have to sum these two. Right? But I1 is going the other way around. This is what? Clockwise or counterclockwise? Clockwise, no? Clockwise. Yeah. But this is going counterclockwise, right? I want to keep the direction same. So basically I1 is just I2 plus I3. Where I1 now I am interpreting as clockwise. Right? So there should be a negative sign here. Okay? I am taking I1 as clockwise. Okay? But what is I2 and I3? It's 2 pi I times the residue at your singularity. Right? And your isolated singularity. So this is 2 pi I times let me call this R residue at what? Z equal to 0. R at Z equal to 0, the residue of function at Z equal to 0. Or there's a way to write it. I think typically people write it like this. R, then you put the function inside, residue of the function at Z equal to 0. Something like that, I think. Yeah, but this is R1 and R2. R1 plus R2. R2, this one. Or when I say R at Z equal to 0 and R at Z equal to Z0. If this point is Z0. Okay? Now do you understand how to integrate an analytic function around any loop containing any number of non-analytic points? Right? Take these non-analytic points, right? But these should be isolated singularities. Okay? Take them, find the residue at each point, and multiply by 2 pi. Okay? And you can deform your contour as whatever way you wish. Okay? As long as you don't include or exclude new non-analytic points, because then you have to add or subtract one more residue. Is this clear? You can have 10 here inside. That's okay. Just take the residue at each point, right? Sum and multiply by 2 pi. That gives you the integral over the entire thing. Okay? Huh? Is this clear? Huh? Okay? This is a very crucial thing. You will see that we'll use this to do real integrals. We'll use this fact to do real integrals. Okay? For example, let me give a quick example and then we can wrap this up. If I integrate a function over this kind of loop, imagine that this is a circle of radius r and r is like infinite. Okay? Huh?
Yes, sir.
And the other part of the curve is this real line. Okay? What is the integral on the function? So what is the integral over this loop? F of z dz. What is this integral? It is, we integrate from minus infinity to infinity dx f of x. Sorry, f of x. Because along this line dz is just dx, right? You are just integrating along the real line. Plus some integral over this circle of radius r. F of x. These two, right? Semicircle of radius r, right? Let's say if for some reason, one could show that this is 0, this guy, okay? Then this closed loop integral is just what? My real integral, right? But this is what? This should just pick up what? Residues. Do you get my point? This should just pick up residues, whatever non-analytic points are here. Is it fine?
Yes, sir.
Huh? Yes. Huh? So we will use this, we will do more concrete examples. This is just to tell you where it is useful. Huh? Let's say if you want to do something like this, minus infinity, dx 1 divided by x squared plus c squared. You want to do this, right? You integrate over this, over this loop, right? Huh? But you consider this 1 divided by z squared plus a squared. A is some number. A is some number. Okay? Then you see that the denominator, let's look at this. The denominator goes as what? If I consider this function, dz 1 divided by z squared plus a squared. If you compute this, look at how the denominator goes. It goes 1 by r squared on the circle, on the semicircle. Right? Huh? But the numerator also goes as r because there is a dz. Remember? Z is r e power I theta on circle. Right? If r is very large, this a is irrelevant, okay? Then this just goes as 1 by r square, right? Yes. The denominator. But dz will also give you 1 by r, right? So what does the overall integral go as? It goes as 1 by r. When you take r to infinity, what will it go? 0, right? So this thing has an integral over this 0, right? Like I said. So integral this is equal to integral over this closed loop, which is just you have to just pick up the residues, right? And what are the poles? X square plus a square equal to 0, which is x equal to plus minus iota a, right? There are only two poles, right? This is where the denominator blows up. You just learned, right? Huh? And both of them are simple poles. Simple poles, right? So you just have to pick residue at whatever, one of them, because the other one will lie outside. Right? See this integral, it just reduced to computing some residue. Okay? So let me write down the final punchline. The integral over an analytic function of an analytic function around any closed loop is 2 pi I sum over residues. 2 pi I times sum of residues. At what? At the isolated singularities that are enclosed by C. This is the punchline. Right? And you saw, you got a sneak peek into what we are going to use it for. We are going to use it to compute real integrals. Okay? You will also see that the Fourier transforms are naturally designed to be done this way. We'll do that later. Okay? So is this clear? Any doubt? Huh? Huh? Okay? So maybe next class I will revise and clean up. But please do revise, okay? At home.